My name is Jayesh Patel and today I'm going to explain bendable memory made from nanowire transistors. These are outlines of for my presentation today. First we're going to go for introduction, then nanowires, then what are nanowire transistors, evolution of nanowire transistors and their IV characteristics, nanowire as a memory storage element and nanowire memory cell. Also we're going to look for non-volatile memory using nanowire transistors, and then we're going to take an overlook of a bendable memory made from nanowire transistors, their advantages, disadvantages, applications and conclusions. Diverse functionalities of semiconducting nanostructures offers the enormous potential for creation of a nanowire field effect transistor, serving as the basis for integrated electronic memory and switching devices that go beyond the inherent limitation of a conventional semiconducting devices. Numerous devices based on a one-dimensional nanostructure has been realized recently, demonstrating unique capabilities for next-generation electronic systems. In particular, nanowire FETs are attracting significant interest as a key component for a logic circuits and memory devices because of the ability of a precisely modulate channel conductance and threshold voltages of a FETs through the surface engineering of a nanowire. This controllability he provides a promising route to range of functionalized memory devices based on a simple low temperature fabrication process that in turn allows for an application on flexible plastic substrate, and this flexible plastic surface then makes a perfect base for bendable memory storage devices. Now let's take a look at what is a nanowire. A nanowire is a nanostructure with a diameter or a lateral dimension in order of nanometers, that is 10 to minus 9. Length of the nanowires varies from a few atoms to many microns. Also, the ratio of length to width is greater than 1000, that is length is very much greater than the width. Material that can be used to make a nanowires are silicon, germanium, gallium arsenide, zinc oxide and indium oxide. And there are other few semiconductor materials that can also be used to make a nanowire. uh, the metals that can be used to make a nanowires are silver, gold and copper. Now depending upon the size of nanowires, different names were assigned to it in literature. One is the viscose fiber, that is a one-dimensional structure ranging from several nanometers to several hundred microns. The other is, as we know, nanowires, that has a large aspect ratio of greater than 20, and the others are nanorods, which has a small aspect ratio less than 20. Uh, then we have the nanocontacts, that are short wires that bridges between two large electrodes. Nanowire also show particular electrical properties due to their size. Unlike a single-wall carbon nanotubes, whose motion of electron can fall under the regime of a plastic transport. That means that electron can freely travel from one electrode to the other. Whereas nanoconductivity is strongly influenced by edge effects. The edge effect comes from atoms that lay at the nanowire surface and are not fully bounded to neighbor atoms like the atom within the bulk of the nanowire. The unbounded atoms are often a source of a defect within the nanowire and may cause the nanowire to conduct electricity more poorly than the bulk material. As the nanowire shrinks in size, the surface atom becomes more numerous compared to the atom within the nanowire, and edge effect becomes more important. There are some applications of nanowires, that is, nanowires can be used for as nanowire FETs, nanowire LEDs, and can be used for memory cells also. Now let's take a look at the evolution of a nanowire transistor. Silicon-based CMOS planar FETs has been used as a mainstream IC technology for over 3 decades. But industry has been addressing great challenges, and several bulk silicon-based device technology has been proposed, such as double gate FinFET and omega FinFET. Double gate FinFET with a gate length as small as 10 nanometer were demonstrated in 2002. However, serious processing difficulties such as a nanometer scale, thin SiO film preparation, pushed to the limit photolithography, line edge roughness, and 3D fabrication makes this new device architecture extremely difficult to manufacture in mass quantity. So researchers find a new technology that is called Nanowire FET, which was considered a strong candidate as it was compatible with current CMOS process and it was having a good controllability of leakage current and was having a high drive current, but the main reason to move toward a nanowire FET was easy manufacturing process at a room temperature. Nanowire FET using nanowire wire is shown in figure here. It consists of a gate, drain, source, channel and an insulator. The current from the source to drain is turned on and off by the voltage applied to the gate. Because the gate in the nanowire is surrounding the channel, it controls the electrostatics of the channel more efficiently than the conventional MOSFET, and because of this is the off leakage current is reduced by a larger scale. Let's take a look at IV characteristics of a nanowire transistor. IV characteristics is a graph of a drain current to the drain voltage. As we can see in this graph that IV characteristics of a nanowire transistor is very much similar to conventional MOSFETs. Hence we can easily replace bulky conventional MOSFETs with a small size nanowire transistors. Nanowire as a memory storage element. A transistor architecture as shown in figure using a molecular structure. A nanowire memory cell holds the promise of unprecedentedly compact data storage. Researchers have successfully tested a self-assembled molecular memory device that has potential of holding 40 gigabits per square centimeter, far greater than any kind of a memory made by conventional silicon technology. It is still more compact as each memory cell can hold not just 1 bit data but 3 bits of a data. That means it has 8 separate stable identifiable electronic states. This memory system is quite stable, holding information up to 600 hours, and further work can increase the stability still further. Nanowire memory cell. The molecular nanowire structure is shown in figure. Indium oxide or indium sulfur or zinc oxide nanoparticles are used to make a nanowire transistor. The channel of the nanowire transistor is functionalized with redox active molecule. Programming in a nanowire transistor can be done by acting on a substrate control voltage. As explained in the above section that there may be 3 or 4 distinct states depending upon the applications and a memory storage specification. By controlling the voltage, it is possible to change oxidation or reduction state to activate or deactivate the molecule, and hence this way a programming is done in a memory cell. Now in order to read out we have to measure the conductance of a nanowire with a gate bias fixed at a 0 volt or a smaller voltage level. Two states can be defined. One is a high conductance that is considered as on state, and other is low conductance that is considered as off state. Now the main advantage of this kind of memory is that it has a high density. Second, it has a simple manufacturing process. Then it has a multi-level storage. But the main disadvantage is low retention time. Multi-bit memory operation in zinc oxide nanowire field effect transistor. Figure A shows switching characteristics of a device with a top gate structure measured with VDS equal to 0.1 and VG equal to 0 volt, clearly showing that ferroelectric field effect transistor functions as a 2-bit memory with 4 different conductance states defined as 00, 10, 11 after the application of gate voltage pulse of -25 volt, +12 volt, +15 volt and +25 volt respectively. Figure B shows a schematic view of simplified polarization model of ferroelectric surrounding a nanowire. The line shows the electric field distribution between a zinc oxide nanowire and a gate electrode. Electric dipole moments are reoriented along the electric field line, resulting in different polarization states according to the gate electric field strength. Furthermore, more dense equipotential lines around the upper part of the nanowire easily induce more polarized charge at the ferroelectric and nanowire interface, resulting from more amount of reoriented electric dipole moment. Thus, different conductance states result from different net amounts of the applied voltage electric field strength. Now I will move towards the final section of my presentation, that is a bendable memory made from nanowire transistor. This memory is based on a principle that I had explained in my presentation and above. Researchers in UK have made a new kind of a nano scale memory component that could someday be used to pack more data into gadgets. This device stores a bit of information using conductance of a nanoscale transistor made from zinc oxide. This flexible memory device is fabricated on a single silicon substrate. The nanowire device stores data electrically and in a non-volatile form, that is, it retains data when power is turned off, like the silicon-based flash memory found in smartphones and memory cards. The new memory cannot hold data as long as flash, and it is slower and has fewer rewrite cycles, but it could potentially be made smaller and packed together more densely. The main advantage of this kind of memory is that it uses a simple process at a room temperature, which means that it can be deposited on a top of a flexible plastic material. Nanowire memory could, for instance, be built into a flexible display and could be packed into smaller spaces inside cell phone, MP3 players, plastic RFID tags, and credit cards. Flash memory element contain a transistor that stores a bit of data as 1 or a 0 using the presence or absence of a charge on a gate electrode. However, like other silicon-based electronic device, flash faces physical limits in terms of how much it can be miniaturized. Memory elements are already at a 25 nanometer, translating to data densities of 1 terabit per square inch, and are projected to reach their minimum size. Companies are increasing flash memory densities by packing twice the amount of data by storing 2-bit or 4 values in each cell, 00, 01, 10 and 11, and this can be done using a nanowire device which can store 4 values as a different level of conductance. It is based on a zinc nanowire transistor, which the researchers make by placing a nanowire on a silicon substrate and depositing source and drain electrodes at the either end of the view. They coat the wire with a barium titanate nanoparticles and deposit an aluminum gate electrode layer on top. A positive gate voltage builds up positive charge on each nanowire and put the device in a high conductance state. a negative voltage switches it to the low conductance state. The researchers used four different voltage levels to create four conductance states. Others are exploring various approaches to make flexible nanoscale memory that could be scaled down beyond silicon. Memory elements based on transistors made from ferroelectric coated graphene, carbon nanotube, and other nanowires could all eventually be made flexible. Some groups have made flexible memory using organic material as well as two electrode device based on thin film of titanium dioxide and graphene. Compared to the zinc oxide transistor, which have three electrodes, two terminal devices can be packed more densely and potentially even in 3D structure. Main applications for bendable memory using nanowire transistors are cell phones, MP3 players, plastic RFID tags, and credit cards. And there are many other space research applications where this kind of memory will be very useful. Thus, we can conclude that unlike a conventional memory device, the electrically variable behavior of a bendable nanowire transistor memory reported herein with a great importance in realizing a flexible, functional, non-volatile memory with a multi-bit memory storage ability and excellent memory performance as with the advantage of simplicity with only a few device fabrication steps and a low temperature fabrication process are required. And this approach is expected to be an attractive potential strategy, providing the high possibility of implementing snaps like devices requiring electrically variable properties. These are the references that I used for making my presentation. Thank you.